everyone! In this video, we will explain how to drive the smart knob of esp32S3 with 2.1-inch screen. This knob needs to have two parts of the drive. Part of it is the rotary encoder. This is an input to the device. The rotary encoder is the physical part of the knob, can rotate left and right. Then enter some parameters for this knob screen. In addition, this knob also has a button function. This button is what we usually think of as an ordinary button. Such a device requires some drivers. In addition, the core of the 2.1-inch screen, the driver IC of this screen, we have listed. It is an IC of GC9503V. We need it to be an IC in RGB format. We need to drive this IC so that the knob screen can display normally. Our work here is based on the first one. We turn on the Arduino. First of all, you can see that the first one is about the header files of some libraries used in our project. The first thing we need to explain is -rencoder.h. We used an MD rencoder library to drive the rotary encoder of this knob screen. This library is also relatively simple to use. First, let's look at this definition. TFTBL is a pin of the backlight. It has nothing to do with the rotary encoder. This is used to drive the screen. The following three pins are the core pins of the rotary encoder. One is button. Button is the pin of the button on this rotary encoder. That is GPIO0. Then the encoder needs to have two pins 5 and 6. Through this library, we can drive the encoder. In fact, the encoder driver is relatively simple. Just use this function to initialize the rotary encoder. You can take a look at this function. This code is the core driver of the rotary encoder. After driving the rotary encoder, some operations can be performed. Of course, the rotary encoder driver only reads the information of the rotary encoder. How to connect a rotary encoder to the LVGL interface? There are two ways we usually see. One is to connect the rotary encoder device to LVGL through the driver, like our touch driver or screen display driver, through the interface provided by the LVGL library. Then make a driver, package it into LVGL, and communicate together. Of course, this approach is not very flexible for rotary encoders. We tried this drive. It requires the main function of LVGL. Just need a LVGL group. Add small controls that need to be adjusted or selected with the rotary encoder to the group. Only those in this group can be selected or switched by the rotary encoder, so it's not particularly flexible. We used another method. That is, we directly read the parameters of the rotary encoder. Then we call some functions related to LVGL that we need to operate by writing functions as a driver that is equivalent to our own. You can take a look at the setup. The initialization of the rotary encoder is also relatively simple. One line of code can drive it. Then we call the value of the rotary encoder to be used in a loop. It is equivalent to a cycle. We delay 5 milliseconds and then read a value of the rotary encoder. For example, the value of the encoder can be read directly using the read function. You can see that this is relatively simple. If the rotary encoder is greater than no, that is it left-handed or right-handed? Left rotation is greater than 0. Right rotation is less than 0. We can use this to judge. Is it switching to the next screen or the previous screen? This screen switching is actually a function we customize to operate LVGL, used to switch screens. Then we achieve the purpose of driving by judging the state of the rotary encoder. In fact, the use of rotary encoders in this part is relatively simple. We directly read the status of the rotary encoder. Use this state function to control the switching of the LVGL interface. Then its button is also relatively simple. We can directly use digital read to read the state of this button. After we read this status, a judgment based on whether it is low frequency or high frequency. To read and switch a state. After reading the status of this button, let's decide what to do. If it is low frequency grounding, that is, after pressing, we switch this indicator. Set to true, that is, we set this Bollinger to true, that is, after we press. It performs an automatic switching process. Because we don't connect it directly to LVGL. It is only driven by an intermediate function, so the code of the rotary encoder is distributed in various places. Looks like more, but in fact, it is relatively simple to drive. The first step is to initialize the rotary encoder. That is, the initialization of several of its pins. Mainly, the 2 pins of the rotary encoder need to be initialized. Its button does not need to be initialized. In addition, reading the rotary encoder can be read with a read function, thanks to our use of mdrencoder. In the previous example, we can find the mdrencoder library. You can search in the library manager next to it and find it. If this search does not find, maybe it is not included in the Arduino list. You can search on GitHub because we've already installed this, so there must be a search. Another part is that we use the GFX for Arduino library to drive this to 0.1-inch screen. This screen is an RGB screen. It is also driven by a RGB565 driver. First of all, it still uses a function of SPI because it needs SPI plus RGB. The SPI function is a simple definition of the 3 pins of SPI. The others are not used. In fact, this value is -1. There is no problem if you write -1. Of course, this is a custom one in this library -1. Then the next function is a function of RGB. That is to define the pins used for RGB, including some common operation pins, including the pins corresponding to the RGB channels corresponding to the RGB values. R is 5, G is 6, B is also 5. It is the 5-channel R, 6 channels of G, then the 5 channels of B. If this order is reversed, the color will not display properly. Then there are some parameters about the screen display. These parameters must be set correctly so that the entire screen can be displayed correctly. The last function is to call some parameters of the RGB screen. For example, its resolution is 480x480, including some operations of its initialization. Here we will focus on the initialization operation, because each screen IC manufacturer makes some adjustments based on its own screen. There may be many optional parameters in the manual of this IC. Different manufacturers may choose different parameters as initialization. For example, there are some parameters. It has several optional parameters. Each manufacturer has different fixed parameters. If we don't know these parameters, there is almost no way to drive this screen. Of course, there are some common parameters that are the same. For example, many manufacturers may refer to the same initialization parameters, then did the same screen. Its hardware is exactly the same and the parameters are exactly the same. In this way, the same initialization parameters can be used to drive. If you make some changes with the initialization parameters, if the initialization parameters here do not match the initialization parameters of the screen, that's impossible to use. Here you can see, we use an initialization parameter with the name. We can find this initialization parameter. You can take a look in the GFX library for Arduino. We have a GFX library for Arduino. Then find Arduino RGBDisplay.h in the src display directory. Here are its initialization parameters. For example, we use the first initialization parameter GC9503V underscore type 1 underscore init underscore operations. You can see that there are many initialization parameters, but its format is consistent. For example, the simple formats above include a command written. Then there is a division parameter. There are some other formats. You need to convert the parameters of the screen you get into this parameter, or the factory parameters given by some manufacturers may be in this format. Just change them one by one. Maybe the parameters are not consistent. You need to apply the parameter format to this format. Each row does not need to correspond to each other, just need the format to match. For example, there are several. You can see that this is a. Then there is another. Adjust your parameters according to these formats. Some screens are very long. For example, GC9503 is a relatively long parameter. Here its parameters end. You can see that it has an end marker. Apply this format. In addition, this library also provides several. For example, there is a type _2, which is also based on the above parameters. It is the same IC, but with different parameters. You can refer to it to change. You can see that this parameter is very long on the edge. Let's drag it and see what type of IC the next parameter is. You can see that the next one is ST7701. GC9503 has two parameters. You can try these two parameters. For example, if you have a 9503 chip, you can try these two parameters to see if they can drive. If both parameters are not acceptable, then you need to ask the manufacturer for the parameters corresponding to your screen. Then create a new one with these parameters. For example, this is type _2. Create a type _3. Then write all the parameters in for debugging. Generally speaking, as long as your drawing parameters are correct, this should be driven correctly. Okay, this video ends here. Thank you for watching.